All right, so this is a review over stoichiometry. I've got moles to grams, I've got grams to grams, liters to grams, limiting reactant, and percent yield. So let's get started. So in our problem here, it says that the fat tristearine is stored in camel's humps. It's used as an energy source as well as a source of water, because when it gets burned, we get this chemical reaction here, this combustion reaction that is labeled and balanced for us already. So the problem is how many grams of oxygen. So I'm going to put an arrow up above that to remind me that it goes on top. So how many grams of oxygen is required to use up or consume 1.4 moles of tristearine. Okay, tristearine is this lovely monster. Okay, this is my tristearine. And I'm going to just call that a big capital T because I don't want to have to write that all out in my train tracks. So start off with my train tracks. Okay, here's my given. So I'm going to put my given up here. So I've got 1.4 moles of my tristearine, which again is T. In here, I'm going to post, this is going to be my ratio. So notice how, because I'm already in moles here, I do not have to convert anything from grams. I don't have to do anything with the molar mass of this big monster for today. So I need to get to grams of oxygen up here though, right? Because that's what this says, grams of oxygen. So I need to look at my ratio. So I'm going to be looking at my ratio between here and here. So upon looking at that ratio, I see that oxygen has, for every 136 moles of oxygen, I have 2 moles of my tristearine. So 2 moles of the T on the bottom, so notice how I have T, both cancel off, is, you know, we've got the ratio of 163 moles of oxygen on top. So now I'm out of moles of my tristearine. I need to get to grams of oxygen, so I know that 1 mole of oxygen is equal to 32 grams. Where I get that 32 grams is oxygen has a mass of 16. I have 2 of them times 2, so that gives me my 32. So now to calculate this, I plug into my calculator, I multiply everything in the top and then divide by everything in the bottom. And when I do this, I end up with, so I have 1.4 times 163 times 32, and I'm going to divide all of that by 2, and I end up with a total of 3,651.2 grams of oxygen. Okay. All right, so on to the next. Okay, in here we've got our equation. It needs to be balanced, so let's balance that out really quick. So I have 1 copper here, 1 copper here. So those seem to be good. I have 2 NO3s here, right? 2 of my NO3s. I only have 1 here, so I'm going to put a 2 here. Now I have 2 silvers here, and I only have 1 here, so 2. Looks like everything is balanced. Okay, I'm going to leave these blanks, but if you wanted to, you could put 1s here as a placeholder to tell you that you have 1 of each of those, but by leaving it blank, you are also saying the same thing. So let's go to our problem. So it says how many grams of silver, so again I'm going to put that up arrow over here to remind me that goes on top, is produced when I use this much copper. So I'm going to set up my train tracks. And I'm going to put my given on top. So I've got that 76 grams of copper. Okay, and I'm going to put the my grams of silver on top here. So grams of silver on top here. So if I go to a periodic table, I can look up and find that the masses for copper is not 44, is 63.5. So 63.3 grams. Okay, and that's equal to 1 mole of copper. And if I look up my molar mass of silver, I see that silver is 107.9. I'm going to round it to 0.9. So my ratio goes here in the middle. So I'm looking at both copper and silver, so I'm going to be looking at the big numbers out front of that. So copper has nothing in front of it, so that means there's a 1. Okay, copper up here, so I'm going to have 1 mole of copper in the bottom, and then I'm going to put this 2 up here in the top, so 2 moles of silver up here. So I have my grams of copper cancel off, I have my moles of copper cancel off, and I have my moles of silver cancel off. So just to figure out this answer, which I'm going to write down here, again, I'm going to multiply everything on the top together and then divide that number by everything in the bottom. So I end up with 76 times 2 times 107.9, and I'm going to divide that by 63.5, and I end up with 258.3 grams of silver as my answer. Alright, going from grams to liters, so again I need to balance my equation up here. Okay, I'm going to rewrite my water here as HOH. Okay, so that I can balance out this H here with the hydrogen here, the OH here with the OH here. So you can see that I have 2 H's here, I only have 1 here, so I'm going to put a 2 here, which means now I have 2 OH's here, so I need to put a 2 here, so I have 2 OH's, 2 NA's here, and I need to put a 2 here for 2 NA's. So again, there's an invisible 1 there. If you would like to put a 1 in front of it, you can as a placeholder, but you do not have to. So if I draw out my train tracks, I end up with, I'm going to start with my 3.76 liters of hydrogen, so of H2, as we can see here. And I want to know the mass of sodium. So again, sodium is going to go on the top, so I'm going to put grams of sodium here on the top. So sodium has a mass of 23 for 1 mole. Ratio. Okay. Because I have this magical acronym here for STP, I can use, because I'm talking about a gas at STP, that 1 mole is equal to 22.4 liters. So now I have my liters of H2 cancel off. Okay, so ratio between H2 and Na, so I end up with 1 mole of H2 on the bottom, 2 moles of Na on the top. So moles of H2 cancel off. I have my 2 moles of Na here, Na, they cancel off. So for here, I'm going to multiply across the top, divide by the bottom. So I put 3.76 times 2 times 23, and I'm going to divide that by 22.4. And I end up with a total of 7.72 grams of sodium. Liters to liters. Okay, we need to balance our equation really quick. So I have 4 here. So I'm going to put a 2 here. I have 1C, 1C, so I have 2 O's here, plus 2 from here is 4, so I'm going to put a 2 here. Okay, ones, you can put them in as placeholders if you need to. If not, you can leave it. So, cool thing about liters to liters is if I set up the really long train tracks, right, I end up doing, I have 4 liters, and then I'm trying to get to liters here. So liters of methane of my CH4, I've got liters of oxygen here. So in the meantime, what I end up doing is I have 22.4 on the bottom here. Okay. And I have 22.4 liters up here. My ratio of O2 to CO3, I get 2 to 1, or CH4, not CH3, is CH4. What happens is, you can see, is we end up multiplying and dividing by NH4, or 22.4. So those can cancel each other out. So really what I'm left with is just the mole ratio. So this is just mole ratio. Okay, so really what you end up with in the end is you just take 510 and you're dividing it by 2. So you could originally just have written this like this, just with the mole ratio. So 2 of your O2, 1 of your CH4. So you're going to just take half of 510, which gives you 255 liters of your CH4. For limiting reactant, what you're going to do is you're going to set up 2 problems. You're going to set up one problem from going from nitrogen to our dinitrogen monoxide, right? So dinitrogen N2O monoxide, O1O. And then you're going to set up another one going from 80 grams of oxygen to our product. So I'm going to write my balanced equation. So I have nitrogen plus oxygen. Please remember that these are both diatomic, so you need to make sure you have those little 2's in there, or balancing is going to be really tough. So you have N makes N2O. Okay, I have 2 O's here, 1 here, so I need to put a 2 here. I have 4 N's here, I need to put 2, so I have 4 on that side. Now I am balanced. So now I'm going to set up 2 problems. One going from 55 grams of N2, 2 grams of N2O, and this one I'm going to go from 80 grams of O2 to, again, grams of N2O. So to set these up, 14 for a mass of nitrogen. I have 2 of them, so that's going to be 28 grams on the bottom here. Again, if you don't know your masses, look them up on the periodic table. My ratio is 2 to 2 for my balanced equation for every 1 mole of my N2O. So that's 28 plus 16. So 28 plus 16, that gives me 44. So my mass is 44 here. So that means my mass is going to be 44 here as well. Okay, so mass of each oxygen is 13, so times 2 is 32. My ratio is 1 to 2. So for this, you're going to do the math. So again, multiply across the top, divide by bottom. So I have 55 for the top one, 55 times 44. I'm going to, this cancels each other out. So this is really just a big old 1 here. So I'm not going to multiply or divide by 2. So I did 55 times 44, and I'm going to divide that by 28. And I end up with, for this top one, I end up with a 86.4 grams of my N2O. For the bottom one, it's going to be 80 times 2 times 44, and I'm going to divide that by 32, and end up with, on this one, I end up with 220 grams. Oh, this wanted liters. Well, we're going to just change this. Since I did the math for grams, I'm going to do it for grams. It's important to read your questions. I didn't read it. So that many grams of my laughing gas. So in the end, what we've discovered, right, for which one is the limiting reactant ends up being my nitrogen, because it makes a smaller amount of product than my oxygen. So once I've made 86.4 grams of my laughing gas, guess what? I have no more nitrogen to react with anything. So it's completely gone. Can't react anymore because I don't have any more nitrogen. So nitrogen is my limiting. So we say this is the limiting reactant because it made the smaller amount. Okay. Final question on here is about percent yield. So percent yield, we're just trying to figure out how close to 100% did we actually get when we did our experiment. So our equation for percent yield is equal to what we actually got over what we should have gotten, which are theoretical, times 100. Okay, so the actual is what we actually got in our experiment. A theoretical, right, you solve that doing math. Okay, so it says that slaked lime is produced when we take quick lime, which is calcium oxide, and we react it with water. So in here I've taken CaO plus H2O goes to my CaOH2. So I just need to balance this. Again, I'm going to rewrite my water to being HO. Oh. Actually, I'm not going to write it as HOH. I'm going to keep it as H2O because I don't have hydrogen on this side as well. So here I'm going to look at, I have one Ca, I have two O's, I have two H's. I'm actually already balanced. So first I've got to do is figure out my theoretical. So I'm going to take my 4,450 grams of my quicklime, so my calcium oxide, and I'm going to go to grams of my calcium hydroxide. Okay. Calcium is 40 plus oxygen is 16, so that's a 56. Okay. Here's my ratio. It's a 1:1 for my CaO to my CaOH. 2, so for every 1 mole of CaOH. 2, so that's 40 plus 32 plus 2. So 32 plus 2 is 34, so 40 plus 34 is 74. Okay. So moles of that cancel off, moles of that cancel off, grams of that cancel off. I'm going to multiply across the top, divide by the bottom. So I'm going to take 4,450 times 74, divided by 56, and I end up with, so my theoretical equals 5,880.3 grams. Okay, so now I need to set it up into our equation here. They gave me how much I actually produced. This is the actual. So I'm going to take my 3,160 divided by 5,880.3, multiply that by 100, and I end up with, so 3,160 divided by 8,880.3, multiply that by 100, and I end up with 53.7%. So that means this process, I'm only making 53% of what I'm actually supposed to make. So that is my quick review of the stoichiometry unit. Hopefully this will help you with finishing up your test and your lab. Please let me know if you have any other questions, and I'll help you out best I can. All right.